All right, let's dive straight in. We're looking at a fascinating new paper from Weick and Fan and team called the Prism Hypothesis.
And it tackles a problem that's been a real bottleneck in foundation models for a while now.
This fragmentation, right, where you have these two completely separate worlds.
Exactly. On one side, you've got your semantic encoders, think Dino, Cli, Epo, that are all about abstract meaning, the what in an image.
And on the other, you have the pixel encoders, like the VAE and Stable Diffusion, which are obsessed with fine detail, the how.
And they just don't play well together.
So this paper introduces the Prism Hypothesis. It's a unifying idea.
It is. The concept is that all natural inputs, images, maybe even text, they all project onto this one continuous shared feature spectrum.
Just like white light hitting a prism and splitting into color.
Precisely. And their big bet is that the semantic meaning lives almost entirely in the low-frequency part of that spectrum.
While all the pixel-perfect stuff, the textures and sharp edges, that's all in the high-frequency bands.
So they built a model to prove it, the Unified Autoencoder, or UAE.
And the outcome is, well, a truly unified latent space. It's state-of-the-art among unified tokenizers, and the reconstruction quality is just off the charts.
I mean, the numbers speak for themselves. The PSNR score over a similar model, RAE, jumps from about 18 all the way up to 29.65 on ImageNet. It's a massive leap.
Okay, so let's start with that initial fragmentation, because it really sets the stage for why this paper even needed to be written.
Right. For the last few years, perception models and generation models have evolved on totally separate tracks.
You had Dino getting great at self-supervised learning for semantics, and VAEs getting really good for stable diffusion, two different goals.
And when you try to force one model to do both, efficiency just plummets. The core issue is a representational conflict. Semantic encoders are built to abstract away the details.
They're designed to throw away information, essentially.
Yes. They treat fine detail as noise because they're hunting for the high-level meaning, the category, the relationships. They live in the low-frequency world.
Which makes them amazing for classification tasks, but terrible if you want to generate a beautiful, crisp image.
Exactly. Then you have the pixel encoders, like in a VAE. They're built to preserve everything all the way up to the highest frequencies. That's where you get texture, sharp edges, geometry.
So trying to unify them is like forcing two incompatible feature sets into one tiny bottleneck. They end up fighting each other instead of working together.
Which brings us to the paper's big idea, the Prism Hypothesis.
Yeah.
It completely reframes the problem. Instead of two separate things, it says maybe it's just one continuous spectrum.
Right. The idea that what we call different modalities are really just different slices of one underlying reality.
Yeah. For an image, the big picture stuff, how objects are laid out, their basic shapes, that's all low frequency.
And the tiny details, the texture on a brick wall, individual strands of hair, that's all high frequency.
And the hypothesis is that the core meaning, the stuff that lets you align an image with text, that almost entirely depends on that shared low frequency base.
So the goal for their model, the UAE, became pretty clear. Build a tokenizer that learns this shared space.
And crucially, anchor the semantics firmly in that low frequency part,
while letting all the complex, messy, pixel-level details live in the higher frequency parts, which the decoder can then sort out later.
It's a really elegant division of labor.
Okay, but a cool analogy isn't enough. They had to actually prove the Prism hypothesis with data before building a whole new architecture around it.
Oh, absolutely. They needed empirical validation. So they found a way to surgically separate these features.
How'd they do that?
They used a 2D discrete Fourier transform the FFT, along with some smooth radial masks. You can just think of them as very precise mathematical filters.
So this let them break any image feature down into its low-pass components, which is like the blurry structural part.
And its high-pass components, which is just the sharp edges and details.
Okay, so let's get into their first big piece of evidence, the frequency energy distribution analysis from Figure 2.
Right. So they measured where existing models were concentrating their representational energy, so to speak. And the results were crystal clear.
What did they find?
The semantic models, Duna V2 and CLIP, they put almost all of their energy right at the very bottom in the low-frequency region around k to 0.
So that's scientific proof that they are focusing on abstract global structures.
It is. And the pixel-oriented models, the VAEs.
Let me guess, they were all over the place.
All over the place. Their energy was spread much more widely, with strong signals in the mid and high frequencies. It just confirms that these models are already sort of naturally separating their focus by frequency, even without being told to.
That's fascinating, and that leads directly to their second and maybe even more powerful experiment, Retrieval robustness.
Yeah, this was really clever. They used a standard text-image retrieval task to see just how much you could mess with an image before its core meaning was lost.
So they would filter the images, either blurring them by keeping only low-pass information, or doing the opposite, keeping only the high-pass edges.
Exactly. And the thinking was, if the semantics really do live in the low-frequency bands, then retrieval should still work, even if the image is really blurry.
And that's precisely what they saw.
It was decisive. The retrieval accuracy barely dropped, even as they filtered out more and more of the high-frequency detail. The system could still match the text to the image.
But what happened when they did the reverse? When they removed that low-frequency base and left only the edges and texture?
The accuracy just collapsed. It fell to near random chance.
Wow.
I mean, that's the punchline right there. Cross-modal alignment, semantic consistency, it's all happening in that shared low-frequency base.
Oh.
The high-frequency stuff is vital for looks, but it doesn't carry the meaning.
So, with the proof in hand, they could finally build the architecture. Let's talk about the Unified Autoencoder, the UAE itself. What I find really smart is that they didn't start from zero.
Right, that's a key strategic decision. Why learn semantics from scratch when you can stand on the shoulders of a giant? They initialized the whole thing from a pre-trained Dino V2 model.
So they're starting with a world-class semantic backbone and then essentially teaching it to care about pixels,
Without forgetting what it already knows. And they do that with a component called the residual split flow.
which is their engine for spectral disentanglement.
Exactly. It takes the latent grid, let's call it Z, and it uses that FFT band projector to mathematically peel it apart into different frequency bands.
Like separating the bass, mids, and treble in a song?
That's a great analogy. And it's iterative, so it peels off one band, and the next band is calculated from what's left over, the residual. It forces a really clean separation.
So you end up with the lowest frequency band holding the smooth global meaning and the higher bands capturing more localized details.
Precisely. And once they have these separated bands, they go into what's called the frequency band modulator.
This is where they do something that sounds a bit crazy. They add noise. Why would you add noise if you want a perfect reconstruction?
It's a very targeted, very clever form of regularization. They know the low-frequency bands hold the precious semantic cargo, so they leave those completely untouched.
Ah, so the noise only gets added to the high-frequency bands.
Only the high-frequency bands. By corrupting the information about texture and edges, it forces the decoder to become incredibly good at denoising and restoration.
It's like a training regimen for the decoder.
Exactly. And that's what leads directly to that huge jump in reconstruction quality. The decoder just gets much more powerful.
Okay, so the bands are modulated, fused back together, but there's one more critical piece, the semantic-wise loss, the LSEM.
This is the seatbelt. This is what makes sure the model doesn't forget its Dino V2 roots.
So how does it work?
It's a loss function that aligns the features from their new trainable encoder with the features from the original frozen Dino V2 encoder. But, and this is the key, it only does this for the lowest frequency bands.
By default, just the first band, right? Band 0.
Just band 0. They're basically saying the global structure and core meaning in this first band must remain identical to Dino's. For the rest of the bands, you're free to learn whatever pixel details you need.
It prevents the model from collapsing into just a pixel pusher. It locks in the semantics.
It's the constraint that makes the whole thing work. It perfectly balances the two competing goals.
Which brings us to performance, because this architecture really, really delivers. Looking at visual reconstruction in Table 1, the jump over RAE is just, it's huge.
RAE was sort of the previous best attempt at this, also built on Dino 2, and it just hit a wall. Its PSNR was 18.05. UAE gets to 29.65. That's not an incremental gain, that's fixing a fundamental flaw in the approach.
And the perceptual quality metric, RFID, tells the same story, dropping from over 2.0 down to 0.19. When you actually look at the example images in Figure 5, what do you see?
You just see clarity. The edges are sharper, the textures are richer, but the best examples are the ones with small text, like a street sign or a document.
Right. Other models tend to blow that into mush.
They do. It's a classic sign of semantic drift. But UAE reconstructs that text with incredible fidelity. It's proof that it's handling both the abstract meaning of the scene and the pixel-perfect details at the same time.
So it can reconstruct, but can it create? How did it do in generative modeling?
Really well. The frequency-separated structure of its latent space turns out to be very friendly for the fusion models.
So you can generate the low-frequency structure first and then fill in the high-frequency detail.
Exactly. It's a much more natural, causal way to generate an image. And they get very competitive scores, a GFID of 1.68, which shows the latent space is robust enough for large-scale generation.
Okay, final check. The whole point was not to sacrifice semantics. Did they preserve the original Dino v2 classification power?
They absolutely did. That LSEM loss did its job perfectly. On linear probing, UAE gets 83.0% top 1 accuracy on ImageNet. That matches the RAE baseline and even beats some larger models.
And the TSNE plots confirm it, right? The clusters look the same.
They look almost identical. The low-frequency band 0 keeps the exact same class separability that made Dino v2 so powerful in the first place. Nothing was lost.
So let's quickly touch on the ablation studies. What was the single most important component?
Without a doubt, the band projector. Just doing that initial spectral split, the factorization, gave them the biggest performance jump. It took PSNR from around 15 all the way to 22. Everything after that was about refining it to get that state-of-the-art quality.
And what about the number of bands? Did they need a huge number to capture all the detail?
That was one of the most surprising findings, actually. No. The whole framework was incredibly robust. Whether they used 2 bands or 10 bands, the performance barely changed.
So most of the important information is in the first few bands.
It seems so. The base semantic band and the first couple of residual bands for detail seem to capture almost everything that matters.
But the finding that, for me, just sealed the deal on their entire hypothesis was when they tested classification on the individual bands.
Oh, I agree. This part is so cool. When they tested only the lowest frequency component, bands 0, they actually got a slightly higher classification accuracy, 83.3%, than when they used the entire multi-band representation.
That's incredible. It's definitive proof. It means all the high-frequency bands, which are essential for making the image look good, are basically just noise when it comes to the task of classification.
It's the whole hypothesis confirmed in a single number. Low frequency is for meaning. High frequency is for fidelity.
So, to sum it all up, the UAE paper really gives us this simple but incredibly effective tokenizer that finally resolves that long-standing tension between abstraction and detail.
It absolutely does. And the big implication here is that it shows how we can take all the incredible knowledge baked into semantic-only models like Dino and successfully transfer it into the world of high-fidelity generation. This feels like a very practical path toward truly unified models.
And it leaves you with a really interesting thought.
It does. Since we now know that the high-frequency bands mostly just carry those modality-specific pixel details, and we know we can manipulate them, we can even inject noise into them.
What does that open up?
Well, what new kinds of applications become possible when you have that kind of surgical, localized frequency control?
You could imagine advanced image editing where you change the texture or style of the high-frequency stuff without ever touching the core semantic layout in band 0.
Or targeted compression. You could aggressively compress the high-frequency bands to make a file smaller, knowing that you're not damaging the core information the model uses to understand the scene. That kind of surgical control over fidelity could really change how we think about efficiency and editing in the next wave of generative AI.